We have finally reached cryptography, and the first fundamental cryptographic idea that we will talk about is symmetric encryption. As previously mentioned, remind yourselves about the approach from the analog world, making use of safes to provide confidentiality to plaintext, and with this, I'm sure you will recognize the conceptual similarities to the symmetric encryption of cryptography as we will now get to know it. What you can see on the left side of this slide is a flowchart, and this is really just the first flowchart of many flowcharts that we will get to see throughout this course. Usually, and unless I'm going to state it otherwise, these flowcharts have to be read from the top to the bottom to understand the proper sequence of actions taking place. What you can now see on the left side of the slide is the flowchart describing how symmetric encryption conceptually works. The key property of symmetric encryption systems is that a single key, which we'll often get to see as named K, standing for key, can be used for both the encryption of a plaintext into a ciphertext as well as the decryption of the ciphertext back to the original plaintext. This property we can clearly also read out from this flowchart, where we see that in order to encrypt a plaintext into a ciphertext, we will need to have a symmetric key K available. The encryption of a plaintext under a certain symmetric key K results in what is called a ciphertext, and this ciphertext is such that to anyone without any knowledge about the symmetric key K used for the encryption, this ciphertext looks like a random piece of data without any relationship to the original plaintext. However, if you are in possession of the symmetric key K that was used to encrypt the plaintext into the ciphertext, you can use the very same key to then decrypt the ciphertext back into the original plaintext. The questions that we still have left to address are: how exactly do these symmetric encryption and decryption processes work? What exactly is the key K used for this symmetric encryption? And what is the notion of security that's associated with such a symmetric encryption process? For the symmetric encryption and decryption processes, many ciphers nowadays exist, but industry standard and NIST recommendation is the Advanced Encryption Standard, which is abbreviated as AES. AES has been standardized by NIST in 2001 and is a block cipher. As a block cipher, AES, just purely and naked by itself, encrypts plaintexts of lengths 128 bits. Although cool, these 128 bits are obviously far from being practically usable, considering that with, for example, the ASCII encoding, 128 bits would amount to just about 16 characters, which would not even be enough to encrypt the title of this course. This is by no means the fault of AES, but is generally the nature of block ciphers, and in order to make these block ciphers such as AES practically usable, plaintexts of length more than 128 bits are split into blocks of length 128 bits, with these blocks of then 128 bits each then fed into the block ciphers such as AES according to a certain block cipher mode of operation. Some of the more famous block cipher modes of operation are the electronic codebook mode of operation ECB, the Cipher-Block-Chaining mode of operation CBC, as well as the Galas counter mode of operation GCM. Many more block cipher modes of operation exist, but these are some of the more famous ones and are also the ones that we throughout this course will have an in-depth look at various stages of this course. The electronic codebook mode ECB is the conceptually most simple block cipher mode of operation. With ECB, each 128-bit block of an input plaintext is encrypted and decrypted in isolation. If we, for example, assume that our input plaintext is 256 bits in length, then the ECB mode of operation splits this 256-bit plaintext into two parts, a first 128-bit block and a second 128-bit block. Each of these 128-bit blocks is then individually encrypted with the very same symmetric key K, resulting in actually two individual ciphertexts, one ciphertext as the encryption of the first 128-bit block and a second ciphertext as the encryption of the second 128-bit input plaintext block. The overall resulting cipher with ECB is then simply the two individual ciphertexts stitched together, resulting overall in a ciphertext of the same length as the original input plaintext. The advantage of this ECB mode of operation is that ECB is conceptually very simple and very fast, as each 128-bit block can be encrypted and decrypted in isolation. However, ECB as a mode of operation is also highly insecure for encrypting any plaintext longer than 128 bits, as equal 128-bit plaintext blocks would result in equal ciphertext blocks and thus would leak information about the original plaintext. As such, ECB as a mode of operation is thus absolutely not recommended to be used in practice and was only shown at this point for educational purposes to give a gentle introduction into block cipher modes of operation. One of the most famous and possibly also one of the most widely implemented block cipher modes of operation is the Cipher-Block-Chaining mode of operation CBC. With CBC, input plaintext of length more than 128 bits, or again in a first step just cut into blocks of length 128 bit, but this time, and as a contrast to ECB, these 128 bit blocks are now encrypted sequentially. The encryption of a 128-bit plaintext block as such depends on the encryption of the previous block. Let's have a look at the flowchart on the left. If we have an input plaintext block of length 256 bits, this input plaintext is first cut into two 128-bit plaintext blocks. The CBC mode of operation then takes the first 128-bit plaintext block and XORs each of these 128 bits of the plaintext block with one of 128 randomly generated bits. These 128 random bits are known as the initialization vector IV. Once all these 128 bits of the first plaintext block are XORed with the 128 random bits of the initialization vector, the result of this XOR is then encrypted with AES under the given symmetric key K. This results in a first partial 128-bit ciphertext for the first 128-bit plaintext block. This first 128-bit ciphertext block is then both part of the overall resulting ciphertext, but also is used as an input into the encryption of the second 128-bit plaintext block, which this time doesn't make use of random bits, but makes use of the 128 bits of the first ciphertext to XOR all the 128 bits of the second plaintext block. The result of this XOR is then encrypted with AES and the same symmetric key, resulting in a second 128-bit ciphertext. The two 128-bit ciphertexts are then stitched together to form the overall 256-bit ciphertext. The advantage of CBC is that CBC is secure if implemented right. A small disadvantage compared with ECB is that with CBC, the plaintext blocks now need to be encrypted sequentially, whereas in ECB, the 128-bit plaintext blocks can be encrypted in parallel. However, it's worth to point out that the actual speed difference between ECB and CBC is marginal, and given that ECB is insecure in the first place, this disadvantage when compared with ECB is ultimately not an argument against CBC to begin with. Having now had a good look at various block cipher modes of operation, the two questions that we still have left to answer are: what exactly are these keys that we make use of during symmetric encryption, and what is the notion of security that's associated with symmetric encryption systems? With AES, the keys that we use are simply bit strings, and AES accepts keys of length either 128 bits, 192 bits, or 256 bits. These symmetric keys to be used with AES can be created by either randomly sampling 128 bits or by deriving the keys from passwords with approved methods such as key derivation functions. In order to understand the associated notion of security, let us briefly remind that the ciphertexts resulting from the encryption of a plaintext look like random bits of data to anyone that doesn't know anything about the symmetric key that was used for the encryption. As such, and if an adversary that doesn't know anything about the symmetric key used wants to decrypt the ciphertext back into the plaintext, the adversary essentially has no other alternative than simply trying all possible keys and checking if the decryption with that key results in a sensible plaintext. If, for example, we would make use of keys of length exactly 1 bit, then this would allow for two keys, the 0 key and the 1 key, and the adversary would just need to brute force across two possible keys to decrypt the ciphertext back into the plaintext. If we had keys of length 2 bits, this would allow for 4 keys. If we had keys of length 3 bits, this would allow for 8 keys. And more generally speaking, if we have n bits, then this allows for 2 to the power of n keys. Hence, for an n-bit key, an adversary needs to try all 2 to the power of n keys, and such an n-bit symmetric key is then said to deliver n bits of security. If we briefly remind ourselves that the number of atoms in the physical universe is estimated to be around the order of 10 to the power of 80, which is roughly 2 to the power of 260, then we can see that if we make use of 256 bit keys, an adversary needs to check 2 to the power of 256 keys, which is an act of almost equally much effort like having to get hold of every atom in our physical universe. Now looking at AES again, AES was standardized by NIST back in 2001 and ever since has been a major source of attraction for cryptographers around the world to break. Even after all this time, current research didn't make much progress over just simply brute forcing across the whole possible key space, with current research currently breaking 128-bit AES in 2 to the power of 126 steps, which is just about a speed up of a factor of 4 relative to the brute force approach. 192-bit AES is broken in 2 to the power of 189.9 steps, again a speed up of just about a factor of 4, and 256-bit AES is broken in 2 to the power of 254.3 steps, which is a speed up of less than 4 relative to the brute force approach. This allows me to conclude, at least based on the publicly available knowledge, that AES in particular is still a highly secure block cipher to be used, which is one of the reasons, not the only one, but one of the reasons why AES enjoys the popularity it enjoys nowadays. Let us quickly think back to the limitation we got to know for the approach in the analog world, making use of safes to provide confidentiality to the data exchanged. There we got to understand that the major drawback for a system making use of safes is the large number of safes required to provide confidentiality to each pair of participants in a group. This drawback directly applies to symmetric encryption as well, as two parties that would like to make use of symmetric encryption for the data to be exchanged between them needs to first have agreed on a symmetric key to be used. Let's look at the examples on the left. If we had just two participants, let's say Alice and Bob, then Alice and Bob need to have agreed on one symmetric key to be used for the symmetric encryption of the data exchange between them. If we also had Charlie next to Alice and Bob, then a total number of 3 keys would need to be agreed on between each pair of the group made up by Alice, Bob, and Charlie. If we had a group of 4, this would be 6 keys to be agreed on, and if we had a group of 5, this would be 10 keys that would need to be agreed on. It's not too involved to derive the formula n times n-1 over 2 to express the number of keys required for a group of size n, and if we apply this formula to a group of 10 people, we see that with 10 people we require already 45 keys, and with 10,000 people we already are looking at almost 50 million keys. Knowing that in modern IT systems such as messengers like WhatsApp and Signal, the number of participants can reach easily into the billions, we can see that symmetric encryption is not a suitable system to provide confidentiality to its participants.